is Christian Kasim-Noor, and I'm a lead data scientist at John Snow Labs and have been working in big data and data science for almost 10 years now. And today I will show you how you can leverage the NLU library to use over 600 state-of-the-art clinical and biomedical NLP models. To understand NLU, we must first understand Spark NLP, which is the basis of NLU. Spark NLP focuses on being the most accurate, most scalable and fastest library out there. And it has accumulated in the 5 years since its release already millions of downloads and has become the most widely used library in the enterprise, is used by many honorable customers and recognized by technology experts by various awards. And so if you look at all of the features provided by Spark NLP and NLU in just one line of code, you can really see why that is so. It has all of the features ranging from simple stemming and lemmatization to the more advanced NLP features like text style transfer, question answering, language classification, summarization of text and text generalization. And all of this is supported in all of the common languages and available in highly optimized builds for NVIDIA clusters with GPUs and CPU clusters. Also, this is available in most of the common cloud environments. And all of this is academically peer-reviewed, checked to be really at state-of-the-art accuracy, and so you can read our papers that explain how we achieve state-of-the-art and also look at our benchmarks. And so, now that we know everything about Spark NLP, let's start with NLU. We will learn about over 600 models and the 50 domains and use cases they cover. And then we will start though with a quick overview and recap of the NLU basics, and following that we will get right into coding and see how we can use each of the 5 algorithms today and all the pre-trained weights, which are named entity recognition, assertion, de-identification, resolution and relation extraction. And so how does it work? All you need to know is there are 2 methods. The NLU.load method, which takes a model name and returns to you a model object, and the model.predict method, which returns to you a pandas data frame. So how would this look in action? You could say NLU.load emotion, and this gives you the model object, the emotion classifier, and then you can say model.predict I love NLU. And this would give you this pandas data frame with 1 column for the predicted category of joy, 1 column for the alternative label of fear and its confidence, and the other confidence columns for sadness, surprise, and the actual sentence embeddings to calculate. And now we can go right into the code. So we can click on this link right here and click on the Jupyter Notebook. Once it's finished loading, we can scroll down and click on this Open in Colab button. And right click it and make sure to open a new tab, or you might run into issues. And so this will open everything for you in Google Colab. And I definitely recommend to you, make sure on the top left you click the table of contents button, which will show you everything we will cover today. And you will see, we will start with an overview, or here you have an overview of all the NER models and domains with hyperlinks to the model hub and more reference links. And you can see there are dozens of NER models, and you see the entities they predict and the labels they give you, and also the spell you need to load them. And then you have all the assertion models here and their domains, followed by all the resolution models and domains, and the relation, and all of course with examples of the predictable label. But instead of going through all of these tables, we will go right away into the code. And so what would you need to do? First of all, you run the first cell to download the install script and run it, and this will set up NLU for you. But we don't have to do this right now because we can just I already did this, so I won't have to do this, but you will have to run this script, of course. And so next you run this cell, which you can use to upload your license for Spark NLP Healthcare. So you need the license to run this. If you don't have one, you can click on this link and get one test license for free. But basically you need to upload the license here, and after you uploaded the license, you can run NLU.out. And this will authorize your environment to use all of the healthcare features. And in case you don't want to upload the file or have troubles with that, you can also manually type the secrets into the text right here and then authorize like that. Okay, and now we can get into the named entity recognizers. And so, how does it work? First of all, an example. So, let's say we have the string Tesla is building factories in Germany. From this string, we can identify substrings which we label as entities, as things of a certain class. In this case, we can say Tesla is an entity and we give it the class of company. Or Germany is also an entity and we give it the class of country. And this, of course, works analogously for many different types of medical domains, like adverse drug events that we can detect. And we could find things like aspirin is a drug, or vomiting is an adverse drug event. Or we can find things about anatomy, cells, chemicals, risk factors, diseases, and much more, which we will check now out in detail. Also demographics, radiology, and many more. Let's say we want to detect adverse drug event related entity. When all we need to do is just say NLU.load and we specify the name of this medical model, and this will return to us the medical NER adverse drug event model. And on this model we can call .predict and give it some medical string, and it will return to us a pandas data frame with one row per detected entity. So in this case we have the first entity is aspirin and it's of type drug. The second entity is nosebleeding, and nosebleeding is an adverse event. So we can also, instead of calling .predict, you can also call .viz on most models. And this lets you also visualize the prediction. And we can see patient reports when taking aspirin, he experiences nosebleeding. That's an event, and we see paracetamol is a drug. Next we get to the anatomy domain, where we can see there are various anatomical related entities and labels we can extract. So we can see here, right, we have a big medical text, and instead of reading it, we can look right away at the extracted entities. We see, aha, skin is an organ, we have the confidence of 90%. Head is an organism subdivision, we have a confidence of 83%. Muscles is an organ, NK cell is a cell, right? And of course we can visualize the same string, and then instead of going through all of this, we can just see, aha, cancerous is a pathological formation, or leg is an organism subdivision, right? Or very easy, how would you get bacterial species, NER? All you need to know is, oh, I just need to specify the name of the model, right? You get the model object and you say model.predict and you give it the medical text. In this case, you can detect, aha, Spirocheta littoralis is a bacterial species, and Neisseria wadsworthi is also a bacterial species. On the other hand, if you are interested in cellular molecular biology and want to get things like DNA or cell types, you could just say medner.cellular.biobird, right? It's the same pattern always. You just load the name of the model, say the name of the model, and then you say model.predict. Or you can say right away model.viz. And then we see, aha, text is a protein, TRE1 is a DNA, GAD is a protein. On the other hand, posology, NER, to get posology related entities, right? And again, this is already straightforward, so I'm not going to repeat this now all the time, but again, what are we going to do, right? We specify the name of the model, we load this, and then with the model object, we're going to say predict. And then what can we also do? We can say .viz, and then we can visualize fragment is a drug, 5,000 units is the dosage of the drug, subconsciously is the route, daily is frequency, and so on. And then of course, if you are a health insurance company or you are in general interested in health risk related entities, you can use the risk factor NER, which lets you extract risk related entities. So you just specify the model, right, the name, and then you call predict or .viz, and then you can extract entities like obesity or hypertension or hyperdemelia or also different types of medications assigned to a patient. And on the other hand, there are also diseases that we can extract with our NER models, and this basically lets us find things like cyst or the death is imminent. On the other hand, there is also, in case you have a medical study and you want to find the tests of patients and also his problems and how they were treated, you could use the general med healthcare model, and with it you could find entities like type 2 diabetes mellitus, which is a problem in the patient, or vomiting is a problem, BMI. You can find those which is a test, right? The body mass index test has been performed on the patient. On the other hand, you can use clinical admission, NER, to find information about admission time or admissions. So in the case, you could say the patient was presented, so the occurrence, to the emergency room, which is the clinical department, last evening, which is a time entity. On the other hand, a very important topic is protected healthcare information, protected by various data laws, and you can extract with the named entity recognizer which entities are protected healthcare information and which type of healthcare information they are. So we can see, Kansas Street is a street entity, Coquille Baptist Hospital is a hospital entity, Olivia is a day patient, or 25 is an 8. So all of these should be protected by your company and all the healthcare companies by the law, right? And on the other side, you also have demographic NER, which lets you find all kinds of demographic data in your data set or information. And you could find things like the gender or symptoms, clinical department or frequency of drugs, and many more. And now there are also, besides those very niche specific models we covered so far, very large and general NER models that cover dozens of different entities. As you can see here, this NER model predicts allergen, EKG, pregnancy, and many more entities. So we can apply this model, right, to a large corpus of text, and we can see all the features, all the information popping up right in front of us. We see the clinical departments, the genders, the hospital name, and much more. And then finally, what I want to show you is there's also an NER for genetics and cancer. And you can use it, of course, to cancer-related proteins and DNA. Also, there is the radiology NER, which finds for you entities that are related to radiological findings and problems. So you can find things that have been found by images, or the directions, or the body parts, or the symptoms. And also genetic variants, which gives you mutations, and protein and DNA mutations, and also SNPs, which are single nucleoid polymorphisms. And this brings us for now to the end of the NER segment, and we come to the assertion models. So what have we learned about NER? It can find a lot of relevant pieces of information in our dataset, and we can use that to filter out all the relevant pieces of text. We can find all the texts, or let's say we have 1 million clinical records, we can find all of them which have a heart attack, right? But now let's say we want to know more. So let's say we have those 3 sentences with a headache. We say Billy hates having a headache, or Billy has a headache, or Billy said his father has a regular headache. All these 3 sentences have the problem entity headache, but only in one sentence the person Billy actually has the problem. And only in one it is currently present. In the other ones, there is no headache currently being inside of Billy. And so we can use the assertion model to give the extracted entity an additional label. So we already know headache is a problem and it's an entity, but now we can assert, is it present or not? So the assertion model would predict for Billy has a headache, the headache is present. For Billy hates having a headache, it would say it's not present, since there is no headache. And for Billy said his father has regular headaches, you could either say not present or it is in the family. And this is what the assertion model is for. It lets you assert the status or get an additional label for the entity you extracted. And so there are different types of assertion models. On the one hand, we have radiology models, which could be something like the X-ray scan shows cancer in the lung. So you can say the X-ray scan is the image test, and cancer is a disease, and the lung is a body part. And you can say the X-ray confirmed the cancer, right? It is present. Or you can say the X-ray shows no sign of cancer. So in this case, the cancer is not present. in the lung, right? Lung is body part, but it's negative. In this case, right, we can visualize the asserted label. On the other hand, we can also say X-ray raises suspicion of cancer in the lung, but does not confirm it. So we can say the problem is suspected, but not present yet. Or we don't know actually, right? Suspected means we don't know if it's present or not. And also final thing, how do you load an assertion model? All you need to know is, since an assertion model is being fed an NER label, right? For each entity we have, right? We assert, we get an extra value. So we input the entities into the assertion model and then get a prediction. And for this, in NLU, we need to specify an NER model. In this case, we specify the NER radiology model, and then you use a white space and say assert.radiology to define that these entities should go into the assert model and be asserted by that model, right? And on the other hand, we could use the general medical assertion model, which can find things like the patient was diagnosed with cancer, so the problem is present, or cancer was shown by the tests. No sign of cancer was shown, so it's absent. Or the tests indicate the patient might have cancer, so it's possible. Or CT scan scheduled for 1999, so a test is planned. Or the patient's legs was amputated in the last year, so in this case it's in the past. Or the patient's father has cancer, and this tells us, aha, the problem is not with the patient but in the family. Or cancer is still possible for the patient, so the possibility. The next segment is the de-identification, and it's pretty straightforward. We basically want to obfuscate and hide all the data that is healthcare protected. So in this case we have a record with the name of the doctor and the name of the patient and his ID and some dates, and we can then anonymize the date, tests, the ID, some other dates, the clinical department, and so on. So this lets you basically protect your data and follow all the data regulation standards. And now we get to the relationship extraction segment. And now we get to the relationship models. We start with a simple example. Imagine you have 1 million medical texts and you want to filter out those which mention patient's left hand being cut off or medically referred to as amputated. We already know the powerful NER algorithm and might think at first, let's filter out all of those texts which contain a direction entity with the value left and a body part entity with the value foot and a procedure entity with the value amputation. With the value hand, not foot, right? And this might sound good at first, but then we filter out things like the patient's left foot and his right hand were amputated, right? And this is a problem. We only want the left hand amputation, but this is talking about left and hand, and this passes our filter, but there's no left hand being removed. So how can we fix this? With the relationship extraction model, we can predict for every pair of entities if or what the relationship between them is. So we can predict that left and foot, those two entities are related. We can predict that right and hand, those two are also related. But we can also predict that left and hand, they are not in a relationship. And also the foot and the amputation is related, but the hand and the amputation, those are not related. And so how can we fix now our problem? Very straightforward. We can define an improved filter that says that we only want those entities where there is a relationship, or those documents where there is a direction entity with value left, which is in relationship with the body part entity with the value hand, and the hand should be in relationship with the procedure entity which has the value amputation. And if you define it like this, you can easily find all the data you need and do all the studies and all the research you might want to wish for. And now we get to the overview of all the relationship models. And you can see we have a couple of binary prediction labels for body parts and different things, but also and also binary labels for adverse drug events and temporal features, but also more complex relationships between chemicals and proteins and drug-drug interactions and posology and more complex temporal features as well. And here you have all the examples that you should check out in detail, but we have to skim them a little bit. So let's start with the first example. First of all, how do you use the relationship extraction models? Very straightforward. You specify an NER model, and then you hit the white space model and specify the name of a relationship extraction model that should look for a relationship within the entities found by your NER model. Right? That's all you need. And then you get one row for each pair of entities and label of relationship for that particular pair of entities. And you can of course visualize this again, and in this case we can see the patient's left foot was amputated. So left and foot have a relationship of 1. Or another example would be body parts and problems, where we would predict 1 if a body part entity and a problem entity are related, and 0 if not. And so a concrete example would be model.this, and then we say the patient reported numbness in the left hand. So we see the numbness problem is inside of the left hand body part. On the other hand, we can also find relationship between body parts and procedures. So medical things we do to the body part. And we say 1 if there is a relationship between body part and procedure, and 0 if not. And also between body part and test. And so we can say the chest was scanned with ultrasound, so the test was applied to a body part, or the amputation was performed on the foot, so the procedure was performed on the body part. And also you can look for adverse drug events with the relationship extractor models, and it will predict a 1 if a drug and a bad event are related together, and 0 if they are not. And so concretely this could be the patient took Lipitor for 15 years, but he experienced severe fatigue. So we see this drug is causing this adverse event. And then also you can find a relationship between phenotypes, genes and diseases. So you can see if a disease is caused by a gene or not. So you can say hearing loss is caused by mutations in the H3 something gene, and also retinal degeneration is caused by this gene. But of course, retinal degeneration is not caused by hearing loss, or vice versa. And of course, you can find relationship between date and tests and results. So you can find out if a date is related to a test or not. The problem is found because of a test. So we can see that the date on 1993 an X-ray was applied to the patient because of a headache, and we found the tumor in the brain. So the date 1993 is the date of the X-ray test, and the X-ray is the tumor in the brain is the finding of the X-ray. Also the headache and also the tumor has been found on 1995. And now the next relationships we can look at are the drug-drug interaction relations, which let you look at basically for 2 drug entities, if 2 drugs are advised to be taken together, if 2 drugs, there's some information about the effect of those 2 drugs, if there's no additional information in the document you're scanning for those 2 drugs, or if those 2 drugs together cause a mechanism, or if there is no interaction at all. And so concretely we could say aspirin should be taken in combination with paracetamol, or Xanax should potentiate the antipersive drugs. So the one is the DDI effect, and it makes it stronger, or avastatin does not interact with chloralidin. So in this case there is no interaction between this drug and that other drug. On the other hand, for posology we can find out a lot of information between entities like drugs and adverse events, or drugs and dosages, or drugs and durations, or forms, or frequencies, or reasons, or routes, or strength. So almost everything you would want to know about posology. So more concretely you would say patient took 5 milligram of felstone, which is the dosage. And of course there's also more complex things like or very powerful again for research of clinical trials or clinical problem tests and treatments, where you can see if a treatment helps with the problem, or if the treatment has made the problem worse, or if a treatment is causing a problem, or if it is administered for a problem, or if the administration of a treatment was avoided because of a medical problem, or you can predict if a test revealed a problem, or if a test performed because of investigation reasons, so to investigate a problem, or two problems are related to each other. So a couple examples could be infection resolved with antibiotic course. So TRIP means that a problem was better because of this medicine. And the next example, there are also very complex relationships between two chemical entities we can find. So two or proteins, so a chemical or a protein together could be part of each other, or one chemical and another chemical or protein could be regulating or upregulating or downregulating or agonizing or antagonizing or modulating or cofactorizing or substrating each other, or not being related to each other at all. And we could extract all of this in detail, but we're a bit short of time, so I encourage you to take a closer look at all of the chemical relationships we can find over here. And finally, also just as a quick overview, there's also more information between dates and clinical entities you could find. Now we get to the resolution segment. So, how can we use resolution and what is it useful for? Let's start with a simple example again. Let's say we use our stock NER again and our company NER, and we have the string Tesla is a great company to invest in, TSLA is a great company to invest in, and Tesla Inc. is a great company to invest in. All those three strings have the company Tesla being mentioned and a company entity. But the actual substring Tesla is not there, right? We have three different strings, and if we were to do some data analytics, we couldn't actually compare them both and be sure that those two companies are the same. In our data, this would show up as different companies, unless we use something like the resolution algorithm, which we can use to define a terminology in our NER vocabulary and basically label each of the possible entity values we could have with a specific ID. So in this case, we could give Tesla the ID of 3, and then we would resolve each of the entities and map each entity to the value 3. So the resolution algorithm takes in as input an entity and gives you a terminological value. And there are many different types of terminologies which work works analogously for the medical domain. So there's like the ICD-10 or ICD-10-CM or the ICD-10 PCS, ICD-O, HCC, CPT, LOINC, HBO, UMLS, SNOMED, and much more. And so let's start with a simple example. Again, how do you use it? It's very straightforward. You just say NLU.load, you specify an NER model, and then you hit white space and then specify the resolver model that should resolve the entities extracted by the first specified NER model. And then you could use something like he was seen by the entomological center and discharged with 50 milligram of Eltron-Bimpark oral at night. So you can see the strength has this ID, Eltron-Bimpark has this ID, oral has this ID, at night has this specific ID, and the frequency has also a specific ID, or metformin has again its own ID in the RxNORM terminology. On the other hand, SNOMED is a terminology for systemized nomenclature of medicine, and we can use it to extract and label things like cancer and give it the label of cancer, or bipolar disorder has a specific label, or schizophrenia has a label, or the Cri-du-Chat syndrome, and of course other disease syndromes we find, right? We get basically for each disease a numbered label. The same works for hierarchical conditional categories. Analogously, right, we get for tobacco or hypertension the labels, or for the CPT, the current procedural terminology, we have resolvers for that, as well as the LOINC, the logical observation identifiers and names and codes, and also HPO and human phenotypes. And of course also UMLS for the Unified Medical Language System, and also various more of the ICD-10, ICD-10 PCS, ICD-O, and SNOMED-CT, and also SNOMED conditions and procedures. And so this brings us to the end of the resolution models and the end of this coding segment and the end of this webinar almost. Here's again, just as a reference, all the NER models overview, all the assertion models, resolvers and relationship extractors. And here's an overview of some of the open source one-liners you can do with NLU that we didn't cover. Things like sentiment prediction, spam classification, question answering, or BERT and ELMO embeddings. Here are some other visualizations and a visualization cheat sheet, and also a cheat sheet for the visualization GUI with Streamlit. And finally, here are some resources about NLU if you are hungry for more. And finally, I would like to thank you for being part of this NLP Summit, and would ask you to please reach out to me if you are interested or want to give me feedback or questions. And I would like to say goodbye.